In this video, we're going to talk about oxidative cycloadditions. The first oxidation we're going to look at is oxidation with osmium tetroxide. Osmium tetroxide, OSO4, can oxidize alkenes into diols. Observe that the product that is produced is a syn product, syn meaning same side. Osmium tetroxide is going to form both syn products or a pair of enantiomers. If we were to do the same reaction with Z-butanoic acid, you would see this product and its enantiomer. T-butanol is just the solvent used for the reaction. Let's look a little bit more at the mechanism. You can see the mechanism here, where the pi electrons from the alkene, and I'll mark those in red, become this bond. Next, one of the osmium oxygen bonds pushes electrons onto the osmium, so those become a lone pair on the osmium. And this osmium oxygen bond comes down to form the green bond shown here. This intermediate, which is known as the osmate ester, is then hydrolyzed to give you both of the products for this reaction. The byproduct for the reaction is then oxidized by the peroxide, the hydrogen peroxide in solution, to reform OSO4. This is done so that way you can use a minimal amount of OSO4. OSO4 is pretty toxic. Technically, the reaction would work if you use a stoichiometric amount, but we usually use a catalytic amount and then use hydrogen peroxide to regenerate the osmium tetroxide, so that way you can use the minimum amount of this toxic reagent. Now let's take a look at potassium permanganate oxidations. Potassium permanganate, KMnO4, can do two kinds of reactions. First, you can see the reaction shown here, where again we are getting formation of a syn diol. The key thing for this reaction here is we are using the cold temperatures. If you increase the heat, this reaction is oxidized further, and we're actually going to get cleavage of the bond shown here. It's helpful to number the carbons. So you can see that the bond between carbons 2 and 7 is cleaved. So here's carbon 2 on the left, and it formed a ketone. Carbon 7 was oxidized to a carboxylic acid. The HCl step in step 2 is just to protonate the carboxylic acid so we don't have a carboxylate. This example is for an internal alkene. A terminal alkene would be further oxidized. Let's look at a terminal alkene. In this example, we have cleavage between our alkene carbons. The carbon I have circled in pink becomes the aldehyde carbon shown here, which is further oxidized by potassium permanganate to a carboxylic acid. The green carbon forms formaldehyde, which is then further oxidized to carbon dioxide. Alkynes can also be oxidized with potassium permanganate. In this case, we have an alkyne, which forms a hydrate instead of a diol, because each set of pi electrons can be oxidized to form a diol. The hydrate reacts then to form a diketone. Recall when we went over hydrates, Hydrates are unstable and quickly react to form the corresponding ketone. If you don't remember the mechanism for this reaction, it's fairly straightforward. In basic conditions, which is what we have here, an alcohol is deprotonated, the electrons come down and kick out an OH. And that would be repeated on the other side to get to the 1,2-diketone product. A terminal alkyne, much like the terminal alkene, can be further oxidized to release carbon dioxide. The bond cleaved is here. And let's number our carbons. So carbon 5 becomes the carboxylic acid. Carbon 6 becomes the oxygen associated with the carbon dioxide. In this case, we have to increase the temperature in order to get this reaction to occur. Next, let's look at oxidative cleavage with sodium periodate and periodic acid. Sodium periodate, shown here, can further oxidize the diol products of osmium tetroxide. So in this case, remember that the alkene is going to form a syn diol after our reaction with osmium tetroxide. So this is the product that you would get after reaction with osmium tetroxide. And then further oxidation with sodium periodate is going to give you the aldehyde product. Notably, the aldehyde is not oxidized to the carboxylic acid like it was with potassium permanganate. HiO4, periodic acid, shown here, could do the same type of reaction. If you have a syn diol, like the one shown, it could oxidize, cleave the bond. In this case, it's the bond between carbons 2 and 6, and that's going to give you a ketone and an aldehyde. Carbon 6, shown here in purple, will become an aldehyde. It is not going to be oxidized to a carboxylic acid like it would be if you use the potassium permanganate method. Let's look a little bit more at the mechanism for this reaction. Here's periodic acid, and you can see that periodic acid forms this cyclic intermediate similar to the one that we saw with osmium tetroxide. And when it falls apart, the oxygen iodine bond breaks and comes down to form an oxygen carbon pi bond. That's this red pair of electrons shown here. The blue carbon-carbon bond comes over to form a carbon-oxygen double bond. Becomes that carbon-oxygen double bond shown here. Then the green electrons from the oxygen iodine bond go over to form the lone pair on the iodine. Our last oxidation that we're going to look at is ozonolysis. Ozonolysis is a reaction with ozone. The intermediate that's formed can then be worked up in a reductive fashion. This is a reductive workup here. And when it does that, this is another method of cleaving that carbon-carbon double bond. You can see the carbon on the left in pink and the carbon on the right in green. In this bottom example, we again have cleavage of the carbon-carbon double bond. Let's number. So we can see that carbon 2 becomes the ketone carbon, carbon 7 becomes the aldehyde carbon, and it is not oxidized to a carboxylic acid because we are using, again, a reductive workup. Reductive workup can include zinc and acid, as shown here, or dimethyl sulfide. In the mechanism for ozonolysis, make sure that you're careful to correctly draw out the Lewis structure of ozone, or O3. Let's follow the electrons. We'll start here at the negatively charged oxygen. The lone pair on the negatively charged oxygen comes down to form a bond, this red bond over here. The pi electrons form a carbon-oxygen bond, shown here in blue. The oxygen-oxygen pi electrons then go over to form a lone pair on that middle oxygen, shown in green here. The malozanide then undergoes a cycloelimination reaction to form the next intermediate. This starts with the green pair of electrons on the oxygen coming down to form the oxygen-carbon double bond, shown here in green. Then I'll draw in pink the carbon-carbon bond coming over to form a carbon-oxygen double bond in pink, shown here. Then the oxygen-oxygen bond breaks, and those electrons form the red lone pair, shown here. In the next step of the reaction, we have another 4+2 cycloaddition. The red electrons come down, attacking the carbonyl carbon because you have a negative charge. That forms the oxygen-carbon bond, shown here in red. The pink electrons then come over and attack the carbonyl carbon. And that forms this pink bond here. Green electrons then go up to the oxygen to form a green lone pair. Reduction with dimethyl sulfide gives the product. In this variation of ozonolysis, we are now using an oxidative workup. This oxidative workup, shown with H2O2, hydrogen peroxide, is going to react the aldehyde further to give a carboxylic acid. So you have to pay attention to the workup that you're using. A reductive workup would stop at the aldehyde, and an oxidative workup will give the carboxylic acid. Notice that you only have to worry about this if you have a hydrogen attached to the double bond. If you don't, you're just going to get the ketone, as we see on the carbon I've circled in pink here. This concludes oxidative cycloaddition reactions, and this is the last video for chapter 24. Don't forget to review the study guide for this lecture and let me know if you have any questions.